Okay, so we've gone through the basics of circle theorems now. We're now going to look at some slightly more complicated questions, and we're going to tackle the tricky question of proof. Let's go! So proof is one of the most important concepts in maths, and the basic idea is that we need to present a step-by-step argument as to why the thing that we say is true in all cases, not just that like we've solved it for one particular value, but for everything. Now this question here says we need to prove that QS is not a diameter. So how are we going to go about this? What do we actually want to do? Well, if QS was a diameter, then that would mean it would have a center on it somewhere. And it would also mean that we'd be able to use the circle theorem that right angles exist in a semicircle. So this angle here should be a right angle. So what we need to do to prove it is not a diameter is approach it the other way. And what we're trying to do is we're trying to show that, what should we call that angle? QPS is not 90 degrees. And if we can do that, that will allow us to prove it's not a diameter. Now we can't draw a center circle on and do things like that because that's things that aren't present in the diagram. So what can we find? And remember, we have to do this step by step. So the first thing I'm noticing is they've identified this as being an isosceles triangle. If that's an isosceles triangle, then we can say that these two angles here are the same as each other, and we can do 180 take away 50 divide by 2 to get that these angles are both 65 degrees. So our step 1 would be to say that what should we call them, XPS and XSP are both 65 degrees, and our reason is that this is isosceles. Okay, so that's a simple argument as our first step. What else can we do from there? Well, we can also use the same segment theorem because we have a sort of a bow tie situation going on here. We can say that QPX, that's this angle here, is equal to 27 degrees. And the reason for that is, as I said, same segment theorem. So again, step by step. Our last step, you can see there, is that QPS is therefore equal to those two angles added together, because we're talking about the angle as a whole, which is 92 degrees. There's no reason there, there's no theorem, it's just we've added the angles up. And we could say, okay, so QPS is not a right angle, therefore QS not diameter. Those three little dots stand for therefore, by the way. I don't know why, but I do know that if you finished a proof, we're going to use the proof square. Statement is proved, QS is not a diameter. Okay, let's carry on. So here's another one. We're trying to show AB is parallel to DC. Now have a think about what that would mean. If AB and DC were parallel, then I think we want to use a parallel line angle, and we could probably say that this angle here would have to be 180 take away 75, would have to be 105. So if we can show that, what should we call it, XAB equals 105, then that'll be enough to show that they're parallel, because then that's a co-interior supplementary angle, whatever we want to call it. They'll add up to 180, and so they must be parallel in the first place. But we can't assume that. We're going to have to use some circle theorems. So what's our step 1 here? What's the first thing you can see? You kind of got circles inside circles here. First angle that I think I'd want to do is this angle here. So what's that? That's XYC. That's opposite our 75, and it's part of a cyclic quadrilateral. So it's equal to 105 degrees. And again, let's put our reason here. Cyclic quadrilateral. What else can we do from there? Well, we can't find this angle, we can't find this angle, but we can find this one. Okay, so what should we call that? XYB. That's 75 degrees. What's the reason for that? It's on a straight line with XYB. And then what else can we do? Well, we can use another cyclic quadrilateral with the small circle this time to say that this one up here is 105. So XAB is 105. It's got to add up to 180 with that 75. So we're using cyclic quadrilateral again. Okay, so let's summarize we're trying to show XAB is 105. We've done that. So we can say, therefore, XDC, which is the 75 down here, plus XAB is equal to 180 degrees. So they are supplementary angles. And therefore, AB is parallel to DC. Proof. Cool, so hopefully you're spotting the pattern here. Now we've got a few more proofs coming up. I'd like you to try and do them yourself. Try and formulate that sort of step-by-step argument. Unpause when you're ready, and then I can obviously look through them. Okay? So there's like, I think, 3 more after this. So here's a case where we're trying to find the size of angle x. This isn't really a proof so much as it is a long sort of step through, but I still want you to approach it in that way. Put your statement and put your reason for everything that you're trying to do. Unpause when you're ready. I'm going to be going in 3, 2, 1. Okay, so my first step would be to say that this here is 24 degrees. How am I going to argue that? Well, it's the same segment with the other 24 degrees. So we'll call that angle FDC. We'll say that's 24 degrees, and our reason, I'll stop putting these in brackets, is that it's the same segment theorem. Okay, I've also got clearly an isosceles triangle here, that's labelled up already. So I can find the 2 other angles in the isosceles triangle by taking that away from 180 and dividing it by 2. Those are both 78 degrees. So I can say DFC and FCD are both 78 degrees. And the reason for that is that this was an isosceles triangle. Okay, so I'm going to have to make a little bit of an assumption here that AC is a straight line, and that would mean that all 3 of these angles add up to 180. Now, is that true? Yeah, I think that is, yeah. So we can definitely use a straight line argument to say that the x plus the 2x, so overall that's 3x, is equal to 102 degrees, because that's a straight line. And lastly, we could divide that through by 3, and we get that x is 34 degrees. There we go. Okay, here's another one. From quite a recent exam paper, this one. X and Y are in the ratio 5 to 7. Work out the size of angle W. And again, we want to step-by-step this. Have a go. Unpause when you're ready. Going to go through it in 3, 2, 1. Okay, so one thing we can say is that X plus Y is 180 degrees, and that's from the Cyclic Quadrilateral theorem. And we also know then the ratio 5 to 7, so we can use add, divide, multiply here to work out what x and y actually are. So if we add our ratios together, 5 plus 7 is 12, divide 180 by 12 to get 15, and then multiply our ratios by that, so we've got 5 times 15 and 7 times 15, we can say that x is equal to 75 degrees, and not w but y is equal to 105 degrees. Reason for that is just obviously ratios. What can we do with that? Well, this would mean that x plus 20, which is in the top of the circle here, is equal to 95 degrees. And so w must be equal to 180 minus 95 degrees, must be equal to 85 degrees. And again, the reason there is cyclic quadrilateral. So there we go. Using ratios. They really love those in the exam for some reason. Okay, last exam question. So we're trying to work out the size of angles x and y. Again, step by step by step, showing you working. Have a go first. Unpause when you're ready. In 3, 2, 1. Okay, so this is a fairly fiddly one. One thing you tend to want to look for is radiuses, and I can see 3 different radiuses in this question. We've obviously also got a diameter going from A to C. So where do we actually want to start here? Well, let's use the isosceles triangle first, shall we? So we've got here 72 degrees, and that means that the other angles in that isosceles triangle must be, 180, take away 72, divided by 2, so that's 54. So overall, this angle is 54. Now, how can we put this as sort of a proof, I'll say? Well, let's say that OD and OA and OC are all the same. And the reason for that is that they are radiuses. So this would mean that we can say OAD and ODA, those are the two angles we just worked out there, are 54 degrees. Reason for that is that this is an isosceles triangle. What can we actually do with that information? Maybe not much at the moment, so let's think what else we can say. We have got a right angle here because we've got a semicircle right angle in a semicircle, that's the one we want to say. So we could say as well that ABC is equal to 90 degrees, and we could give the reason that it's a right angle in a semicircle. Are we getting any closer to what we need to find? Maybe, maybe. What else is a right angle? Well, this is a right angle as well because it's a radius and a tangent. So we can also say that OAT, or OAT, is 90 degrees, and we can say it's a right angle, type that again, between a radius and a tangent. Okay, are we getting anywhere? Basically, yeah. So we can say what y is, can't we? We can get y as being equal to 90 minus 54, so it's equal to 36 degrees. And there's no particular proof of that beyond it's a right angle. So what else can we do from there? So what we can do is we can use same segment theorem, because we can see that we have got our bow tie situation here. Don't think I will erase that. And so this top angle here must be the same as the 30 degrees that we already have on the diagram. So how can we state that? We can say that ACB is equal to 30 degrees, and the reason for that is same segment. Okay, but we do need x as well, so that's fine. We've got a triangle now, so we can go 180 minus 90 minus 30 is equal to 60, so we can say x is equal to 60 degrees, and the reason for that is just that it's in a triangle. If we want to be special, triangle equal 180. Okay, so that's the basic idea of longer form exam questions and how you want to set out your working. So as well as that, we're also asked to prove the circle theorems that we've been using so far. And this has not been examined yet, but it is on the specification. Now, the ruling is that if something hasn't been tested within 5 years, they have to take it off the specification. So I would consider it fairly likely that the next year or two we'll have one of these questions on it, or we'll just have it removed, but we do have to look at it. So here's the first one. It's we want to prove the angle in a semicircle is always 90, so we're trying to prove that this angle here is 90. I'm going to label up my points. I'm going to call this A and B and C, and I'll call the center O, just because it'll make it easier to do those sort of proof setups we've looked at so far. The first thing we're going to do is we're going to split this into two triangles. Okay, so we're going to split into two triangles, and we're trying to explain this proof, succinctly. Now, why did we do that? Well, what that gives us is a number of radiuses, and that means we've got two isosceles triangles here. So we can say, therefore, that AOB and OBC are isosceles. We're specifically talking about the triangles there. And we can sort of label the two angles that would have to be the same. Okay, we'll say that OAB is equal to OBA, which is equal to x. So we'll call that angle x. And we could furthermore say that OCB and OBC are equal to y. Again, purely because of this isosceles fact. Okay, that doesn't seem like it's helped us much. We want to try and get 90 degrees out of this somehow. Well, here's what we can do. We can, at this stage, think about the angle as a whole here as being x plus y. So let's do that. We'll say that ABC is therefore equal to x plus y. We've just added them together. And we know a triangle has to add up to 180 degrees, don't we? So this triangle, the big triangle, consists of an x plus y, and a y. So we can say x plus y plus y is equal to 180 degrees. The reason for that is it's a triangle, and triangles have to add up to 180 degrees. So what does that simplify to? 2x plus 2y is 180 degrees. And what could we do with that? We could halve it. X plus y is 90 degrees. And that's what we wanted, because that's what ABC is. So ABC is equal to 90 degrees. Let's put a therefore on it. Let's put a proof square on it. Boom! Circle theorem proved. Right, so you get the idea. Okay, so let's prove the double angle theorem then. We're actually going to start in exactly the same way. We're going to draw right down the middle a line. I'm going to label these up as being A, B, C, and O. And I'm going to note that drawing that line gives me some radiuses. So let's start. We would say OA and OB and OC are all the same. The reason for that is because they're radiuses. This means we've got isosceles triangles. So we can furthermore say OAB and OBA are both equal to x, let's say. And the reason for that is that we have formed an isosceles triangle. And we can say that OBC and OCB are equal to y, because we formed another isosceles triangle. So far, this is very similar to the previous proof we've looked at. So what can we do from here? Well, we can consider this angle. We call that AOB. Now we know that angles in a triangle add up to 180, but we also know that two of the other angles are x. So if we take them away from our 180, we'll get the AOB that's left over. So we could say that this angle here is 180 minus 2x. Furthermore, we could say that COB, that's this angle here, is 180 minus 2y by exactly the same reasoning. So now we're sort of getting somewhere. I'm just going to move this O a bit more centrally. So what else have we got? Well, the last angle that we're going to try and find is this one here. Okay, we'll call that AOC. Now that, we know that all three of these angles have to add up to 360. So this is going to be the case that if we were to do 180 minus 2x plus 180 minus 2y, and we were to add whatever AOC is, then we would get ourselves to 360 degrees. Well, let's simplify this a little bit. So we've got 180 plus 180 minus 2x minus 2y plus this AOC is equal to 360. Well, we can definitely cancel out the 360s from each side. We can take away 360 from each side, and we can end up with the statement that minus 2x minus 2y plus AOC is equal to 0. And then we could add the algebra across to the other side. We could say that AOC is equal to 2x plus 2y. Now, we're basically done now, because what we've shown is that the angle at the center is 2x plus 2y, and the angle at the circumference is x plus y. So let's state that. We can say that ABC is equal to x plus y. So therefore, AOC is equal to 2 times ABC. Proof made. Boom, another circle theorem down. 4 to go. Okay, so we're going to prove same segment now. And this is actually a bit quicker than the first two we've looked at. Our first step is going to be to add in the center of the circle, wherever it might be, and label that as O. So let's say our first step is to add the center of the circle. Now, one thing we can say about the center of the circle, and let's, I guess, label this up C and D, is that the angle at the center is double the angle at the circumference. So we can say that AOD, that's this angle here, is 2 times ABD. The reason for that is double angle. So this is very much a crossover episode. We are using a proof we have already done. But we could argue the other way as well, couldn't we? We could argue that AOD is twice what ACD is, because it's also a double angle for that as well. So what does that tell me? Well, if AOD is equal to 2 times ABD, and AOD is equal to 2 times ACD, then that must mean that 2 times ABD is equal to 2 times ACD, because that's just combining the statements together. If they're both equal to AOD, then they must be the same as each other. And then we could just divide by 2 and say that ABD is equal to ACD. And that's it. That's the proof. Double angle and done. Okay, so cyclic quadrilateral. Now this is going to again start with drawing on the circle center. So our first step is going to be to add the center of the circle, which we'll call O. Now, what do we actually want to do with this? Well, we want to use the double angle theorem to our advantage here. If we call this A, B, C, D, and we've got O in the center, I can say that ABC is equal to X, and that will tell me that AOC is equal to 2X. So I'm labeling this one as being X, and this one as being 2X. And the reason for that is obviously just the double angle theorem. Similarly, I can label this angle here, ADC, as being Y, and I can use the double angle theorem again to say that the angle over there, I guess it's AOC, but the minor version is going to be equal to 2Y, and that's again through double angle. Now, why is this useful? Well, 2X and 2Y are all the way around a single point. So I can say that 2X plus 2Y are equal to 360 degrees. Our reason will be angles at a point. What can we do with that? We could just halve it. We could say that X plus Y is equal to 180 degrees if we just divide by 2. But look back to what we said. We said ABC is X and we said ADC is Y. So therefore, we're saying that ABC plus ADC are equal to 180 degrees. Opposite sides add up to 180. Boom, another circle theorem proved. Okay, 2 to go. Let's crack on. Okay, so 2 to go. We're going to prove a tangent and a radius meet at right angles, and this is one of my favorite things as far as math proof goes. This is a proof by contradiction. So in English, contradiction is where something you say doesn't match up to something else that you say. And that's exactly how a maths proof by contradiction works. Okay, what we're going to do is we're going to assume that this is not a right angle, and we're going to show that this leads to some sort of unavoidable problem in the time-space continuum. What we're going to say is that, okay, well, if that isn't 90 degrees, there must be some line that comes from the tangent at 90 degrees and matches up to this center. Okay, there must be some line we can draw. So let's label this stuff up. Let's say we've got this as being O, A, and B, and I think I'm going to need this point, so I'll call it C as well. And how are we going to state this? So we're going to assume that OBA is equal to 90 degrees. So if OAB isn't 90 degrees, there must be some 90 degree angle we can draw. Now what's the problem with this? Well, we know about right angles, or right angled triangles, that the hypotenuse, the longest side, is always opposite the 90 degrees. So that must mean that OA is the hypotenuse of this right angled triangle that we've drawn. So if we assume OBA is equal to 90, then that would tell us that OA is the hypotenuse, and that specifically would tell us that OA is the longest side of the shape. So OA is obviously bigger than OB. Now what's the problem with this? Well, the problem with this is that this is a circle and we've got radiuses, and we know that OA and OC are both radiuses. So we can say OA and OC are radiuses and therefore they're equal to each other. And if OA is the same as OC, then this could replace that in that inequality and it would still have to be true. So therefore, OC is bigger than OB. But look what we're saying. We're saying that this distance from O to C is bigger than a line that goes beyond it and travels all the way to B. So that's nonsense. Or let's use the slightly more mathematical word of impossible. So therefore, OAB must be the perpendicular, must be the right angle. There you go, proof by contradiction. Okay, final proof then. We're going to look at the alternate segment theorem. So the first thing we're going to do is we're going to fill in two radiuses that go to the center of the circle. So we're going to draw two radiuses to the center. Well, where else could a radius go, I suppose? Then we're going to label up our diagram a little bit. So I'll call this A and B and C and O. And I'm going to add in one extra bit. So we're going to sort of say, well, let's draw the bisector of this line. Let's draw a 90-degree angle to O. And we can have that meet at some point D. So let's actually say that we've done that. We could say we could split triangle into two right-angled triangles. Cool. Okay, so we've done that. So we know we've got a right angle there. Now, how we're going to actually argue this is we're going to say that OCD, that's this angle here, is equal to x. We're just going to state that. And then we also know that this is a right angle. That's OCE, I guess. So OCE is equal to 90 degrees, and that's because it's a tangent and a radius meet at 90 degrees. We just proved that on the previous slide. And so that would mean that x is equal to 90 take away, let's say, DCE. Now what I think we want to do is define DCE as equal to A, say. So x is equal to 90 minus A. Okay. What else can we do? Well, we could say that angle COD, or COD, getting all the great acronyms out today, is equal to y. We're just going to say it is. And then what's the thing with that? Well, that's part of a right-angled triangle that involves a 90-degree angle, an x and a y. So we can therefore say that x plus y plus 90 is equal to 180 degrees because we've made them into a triangle. And take away 90 from both sides, that means that x plus y is equal to 90. But we know, based on this, in fact we could slightly rewrite that as x plus a equals 90, that x plus a is equal to 90. So if x plus y is equal to 90 and x plus a is equal to 90, then this means that a and y are the same thing as each other, because they both add to x and get to 90. Now, we can do a symmetry argument here, and we can say that we've got another 90-degree angle over here, we've got another y over here, we've got another x over here, and we have overall this angle of 2y at the center. So we can say that COB is equal to 2y. Okay, nearly done. So by the double angle theorem, we know that CAB is equal to 2y divided by 2 is just equal to y. Double angle. And so we can say that CAB is equal to ECB is equal to y, because that was A, that was equal to y, and that's y, that's equal to y. So we have done our proof. Quite a complicated one, that one. Anyway, circle theorems, done.